So today's presentation is focusing on some basics of the Smith chart. I will try to keep it simple. We'll be looking at the paper Smith chart. The name Smith comes from Dr. Philip Smith, who invented the Smith chart. I believe it's somewhere in the 30s. He is a graduate of Tufts University from Boston and held a position at the Bell Telephone Research Division for a number of years. Very elegant method of finding solutions for characterizing transmission lines, matching loads to sources, etc. We can utilize the Smith chart in impedance mode and in admittance mode. Today we'll be focusing on impedance mode applications. The Smith chart initially, if it's your first exposure to it, can be somewhat daunting. It looks very complex, but can be easily broken down. We'll attempt to lay some building blocks for that. We'll follow up with at least a couple more Smith chart examples after that. This is just covering the basic mechanics of the Smith chart, and then we'll have a couple videos on particular applications. So it's important for you to realize that we're breaking this down into resistive and reactive components while we're in the impedance mode. Once again, the outside of the circle, an important point for you to know going into this, is not scaled to 360 degrees. One full rotation has an angular displacement of 180 degrees, as predicated by Dr. Philip Smith in its application to half wavelength variations, which are a particular order of performance by transmission lines, for example, that are unmatched. We have this repetitive and a lossy transmission line environment, this repetitive repetition of half wavelength values, which can be determined by using the Smith chart. So we'll start the slideshow. We'll go to the second slide, and we'll look at the first slide once again. So there's a little larger view of the first slide, and you can see right in the center there's a red dot. The red dot in the center is indicating a normalized value of 1. For example, if you were working or designing in a 50 ohm environment, you would normalize your 50 ohms to that value of 1. So where 1 is also where your 50 ohms is. That's where we want to get to if we want to have a perfectly matched system. And notice that on that line that 1 is drawn on, there's a bunch of circles that intersect it. And then if you follow the circles out, you'll see arcs that are intercepting those circles, and they will represent reactive values. We'll try to break this down better for you in the next slide. So once again, we're looking at impedance mode with resistive and reactive values. Also, admittance mode can be acquired from the Smith chart, which would be composed of conductive and susceptive values. So you can actually build your own Smith chart by starting with a circle. Draw an axis down the center. The axis will be where all the resistive values originate from. It's scaled from 0 to the left to infinity on the right. If you start at the center and draw a circle, you've now characterized on that circle every potential reactive component value that's associated with 50 ohms, or the normalized value of 1. It does not have to be 50 ohms. You may be characterizing it for video application of 75, and it's the beauty of being able to normalize your impedances to the Smith chart. Part 2 shows you how to do that. So you can continue to build resistive circles originating through or off of that axis down the center, and after that you can start to build your arcs that represent reactive values. So the upper hemisphere is inductive reactive, and the lower hemisphere is capacitive reactive. In other words, the upper hemisphere is plus J, and the lower hemisphere is minus J. So it's possible that you can have an R value that's associated with a plus J, or an R value that's associated with a minus J. So once again, in the center we have the normalized value of 1, which most often will be a 50 ohm application, but not always. So there's a couple more reactive arcs. This is by no means perfect scale, but the methodology is correct. Now, take note of the arcs intercepting some of the circles. Where those 2 points meet, you will have a impedance value. For example, where the red line from 1, or the normalized value, intersects the first reactive component, where those two meet, you will have a impedance value, what's called a normalized impedance value. Once again, part 2 will give you a better insight into that. So when impedance in impedance mode, this axis, and the axis that we're referring to is that one, it is used for the normalized resistive values. Now this region that we're illustrating right now can also double as a scale for SWR. So in part 2 we'll show you how to draw an impedance circle, and where the impedance circle draws through that axis down the center, or the middle of the Smith chart, where it intersects that point, that will be your SWR value for your particular scenario. Okay, so we'll go back to the first slide and just do a little bit of a summary. Once again, in summary, we sort of disregarded this in the second PowerPoint slide, but this region right in here are simply some sort of a fraction or value of half wavelength, 0 to 0.49 or 0 to 0.5 actually. And you'll notice there's two sets. The outer one, which goes toward the generator, and the other one will go towards the source. So counterclockwise and clockwise. We'll get into that in more detail in part 2. You'll also notice that right in here we've got angular values. If you look closely at it, it'll range from 0 to 180, not 360, but 0 to 180. And here's the axis that all the resistive values lie on. And for example, you can see this first circle that breaks out from that point. I'll try to draw it as accurately as I possibly can, and there we go. And here, for example, is a arc representing a reactive value. So you can hear this is a value of 2, and it's intercepting a value of 1. So we have a normalized value of 1 plus J2 as an example. If you multiply that by 50 ohms, you'll find out what your impedance is. That's easily done. 50 times 1 is 50, and 50 times 2 is 100. So we've got a unnormalized or real world impedance value of 50 plus J100. Okay, that ends our introduction to some of the mechanics of the Smith chart, and we'll look at a real example of characterizing a transmission line in part 2. Thank you very much.